right, well, let's go ahead and take a look at what we were talking about in our last lesson, and that was multiplying the complex numbers that were in the trig form. If you would, go jot this down on your paper. Actually, you know what? I'll let you be lazy. I'm going to roll off of what I'm doing here. Because it is a pain, let's be honest, to copy these multiplication problems. Let's suppose we had 5 times the cosine of 140 degrees plus I times the sine of 140 degrees times 4 times the cosine of 10 degrees plus I times the sine of 10 degrees. It looks ugly, but the multiplication's really easy. Do you remember what we do first, Quentin?
Multiply the R values.
You start by multiplying the R values together to get 20. Then, Jamie,
we add the degrees together to get cosine of 150 plus I sine of 150.
there we go. Much like multiply the coefficients, add the exponents. It's kind of like a coefficient exponent type of thing. And then from there, we'll simplify. Of course, with the 150, we know that's really 30 degrees in quadrant 2. All right, so then cosine of 30.
3/2.
But in quadrant 2, sine of 30.
1/2.
And of course, don't lose the I. And then quadrant 2 sine is positive. And we'll distribute the 20 to this to get what, Jamie?
10 times the square root of 3 plus 10i. Yeah, 10.
The little negative right here. Don't lose that. All right. And there would be our answer. So a lot faster than the FOIL, in my opinion. Well, I should say a little faster than the FOIL. I'm not going to say it's a lot faster, but a little faster than the FOIL, in my opinion. What if we had a 1/3 times the cosine of 105 degrees plus I times the sine of 105 degrees multiplied by 6 times the cosine of 120 degrees plus I times the sine of 120 degrees. Jamie, how would we start this one?
We would multiply the r's together.
To get?
2.
2. And then, Quentin?
Add the angles to get cosine 225 plus I sine 225.
And then, of course, once again, we'll say what quadrant is the 225?
3.
And the reference angle?
45.
And cosine of 45?
32.
But in quadrant 3?
Negative.
And the sine of 45?
32.
But in quadrant 3?
Negative.
And don't lose the I either. We're going to distribute the 2 to all of this to get, Quentin?
Negative square root of 2 minus I square root of 2.
Square root of 2 minus I squared of 2. Questions on that? Turn your textbooks to page 187. Page 187. I want you to do numbers 1, 2, 3, and 6. Page 187, numbers 1, 2, 3, and 6. Notice on number 1, they want you to take that standard form, quickly convert it into the trig form, and that way you can do your multiplication that little bit easier. This is the way they wanted you to work number 1. Did you get a 3 square root of 2 cosine 135 plus I sine 135?
Forgot about the quadrant with the 135.
So you had 45, which gave you a 90.
I had 45.
All right, questions on that? All right, now the other way you could have done it, admittedly, was to say, well, this is a 1 over square root of 2, and this is a 1 over square root of 2. Now, normally we'd say square root of 2 over 2, right? But if I leave it as 1 over square root of 2, because this is a radical, I can cancel to get square root of 4 plus square root of 4 with an I. That's 2 plus 2i. And then I could FOIL. First, outer, inner, last. That becomes a negative. 1 times 6 is negative 6. There's the exact same answer. So as long as they match, you could multiply them. Okay, it's really kind of up to you there, but this is the direction they wanted you to go. Just wanted to show you the other direction you could have gone. Right? Questions on that? Number 2, a lot more straightforward. We multiply the r's, class. 3, we add the thetas. Good, so your initial answer is 3 times cosine 150 plus I sine 150. And then when we work it all out, we end up getting what here, Jamie?
Negative 3 times square root of 3 all over 2 plus 3i over 2.
Good. Negative 3 squared root of 3 all over 2 plus 3i over 2. Nothing canceled. It's just big ugly answer. We're good to go on that one? Number 6. Multiply the r's, class.
12.
Add the thetas to get.
Cosine 300 plus I sine 300.
Good. And so 12 cosine 300 plus I sine 300 becomes, Quentin?
You want final answer?
Final answer.
Okay, 6 minus 6i times square root of 3.
6 minus 6i times the square root of 3. And then dropping all the way down to number 6. We multiply the r's to get, class.
14.
Add the thetas to initially get.
Cosine 390 plus I sine 390.
But 390 is too big, so we got to subtract 360. It comes back to just
30.
30. So it ends up being 14 times cosine 30 plus I sine 30. We end up getting what for our answer, Jamie?
7 times the square root of 3 plus 7i.
7 times the square root of 3 plus 7i. Good on that? Any questions on multiplying the trig form? All right. If you have questions and you're watching on YouTube, reach out to me, get those questions answered. Don't want you to suffer just because these two are show off. Just kidding. All right. Next thing in your notes, dividing trig form complex numbers. Dividing trig form complex numbers. This is where you start to gain a notable edge on the other form. Multiplication, I said, y'all thought it was faster. I think maybe a little faster. Division was a real pain. Multiplying by the conjugate involved a sum and difference in the bottom. It involved foiling in the top. Ain't nobody got time for all that. And the trig form makes life easier. Understandably, it's going to seem very similar in process to the multiplication. We divide the r values instead of multiply them. Well, that makes sense. And instead of adding the thetas, we'll subtract the theta values. Now, there is the inherent chance that when you subtract away theta values, you could end up getting a negative angle. But then you just add 360. Just like when we added theta values, we had something bigger than 360, you can just subtract 360. So that shouldn't be a problem for us. And then, of course, is it ugly to look at, we'll convert to standard. If you'd had to guess what the steps were, you probably would have guessed those. And you'd have been right. So for instance, if I've got 6 times the cosine of 120 degrees plus I times the sine of 120, go ahead and copy this one down so you've got some examples in your notes to refer to. I can't imagine you blanking out, but that's why we call it blanking out, is because you couldn't imagine it happening. So 6 times cosine 120 plus I sine 120. Now let's suppose we're going to divide all of that by a 3 times the cosine of 75 degrees plus I times the sine of 75 degrees. The book uses the division symbol. I'll usually do the same just to be consistent. Obviously, we normally would show this with the fraction bar, right? Where this would be underneath. You know, so however you see it, this I think is the way the book and therefore I, trying to stay consistent with them, will present it. Don't be surprised if college texts or other things you're looking at have it with the fraction, because that's usually how division's shown. But 6 divided by the 3 class would be 2. And we subtract 120 minus 75, we get
45.
And now we just got to convert it. Both cosine and sine of 45 are square root of 2 over 2. And since it's in quadrant 1, they're both positive. But when we distribute the 2, it's going to knock out the denominator. So we get, and we're done. That is definitely faster than multiplying by the conjugate. The multiplication may be faster, maybe not. This is no question about it. So much faster to work in the trig form than in the standard form. Write this one down. 8 times the cosine of 30 degrees plus I times the sine of 30 degrees divided by 2 times the cosine of 75 degrees plus I times the sine of 75 degrees. First step, divide the r's, we get 4. Next step, subtract the thetas, but 30 minus 75 equals negative 45. Now, if we wanted to add 360, that would give us 315. So we could say the cosine of 315 degrees plus I times the sine of 315 degrees, and that's what I'm going to recommend you do. Now, you might be thinking, well, wait a second. Couldn't I say, instead of cosine negative 45 plus I times the sine of negative 45, couldn't I just say, well, cosine of a negative angle, poof, it's gone. Cosine 45. And here the negative comes out front, negative I sine 45. Absolutely. These are equivalent to each other. My fear is you'd lose the negative. That you'd forget that the negative was there somehow and it would mess you up. You're not as likely here, so that's why even though this is probably easier, you don't have to add 360. Gone, slide it out. I think this is the safer plan. But both of them will work, and you wouldn't lose points for doing this if you feel like, oh, I'm going to live on the edge, man. Anyway. There's this movie I watched, and they had their bonus features or whatever, and the one guy is like a fireman in the movie, and it's like talking about his actual life. He's like, yeah, I always live on the edge, buy a 99-cent highlighter, take the cap off, leave it off all night, I don't care. I just live on the edge. That's what I was thinking. Living on the edge, man. Pulling those negatives out. All right, anyway. So, taking it from here, though, obviously reference angle is still 45. Quadrant 4. And, of course, you're going to see here, here's your positive from quadrant 4. Here's your negative from quadrant 4. Here's your negative. There's your positive. Okay, they're going to come out the same either way. So the cosine of 45, of course, square root of 2 over 2. And it's going to come out positive from quadrant 4. And the sine of 45 is, again, negative square root of 2 over 2, but negative in quadrant 4. And then don't forget the I. We'll distribute the 4 to get
2 times square root of 2 minus 2 by square root of 2.
All right. Again, you pick which one you feel better with the negative angle. Again, no problem using negative angle identities. No problem adding 360. It's your call. Which one you feel more comfortable with. And then sometimes you get annoying ones like these. 5 times the cosine of 250 degrees plus I times the sine of 250 degrees. I'm going to show with the fraction bar this time just for fun. Divided by 3 times the cosine of 100 degrees plus I times the sine of 100 degrees. What makes this one so obnoxious? I think you've already figured out. 5 came divided by 3 evenly. What is 5 divided by 3? 5/3.
1.6.
Oh, no. Stay away from decimals. Decimals are our enemies. We're just going to say 5/3. All right? Times the cosine of, ooh, careful. We're dividing. 150 plus I times the sine of 150. So there's a reminder for you. Make sure we subtract the thetas on the division as opposed to adding them on the multiplication. Keep those straight. Reference angle. In quadrant,
2.
cosine 30.
Square root 3 over 2.
And in quadrant 2,
Negative
sine of 30.
1 over 2.
Quadrant 2,
Positive.
don't forget the,
I.
and then we're going to distribute the 5/3. Well, good news is we already had fractions anyway, right? So we definitely don't want to introduce Jamie decimals and fractions. Very likely this is going to come out to fractions anyway, so we just multiply the fractions. I start by getting,
The common denominator.
no, you don't need a common denominator to multiply, just multiply.
5/3 plus 5 to 33 all over 6.
Negative 5 square root of 3 over 6. We multiply here. Then we multiply here, and we get
5i over 6.
5i over 6. Not pretty, but also not the end of the world if it doesn't divide out evenly. I mean, you're not going to run into that with multiplication. Multiplication always works. Division, sometimes get weird numbers. Oh well. Questions? All right, extra let's do 8, 9, and 12 now on page 187. 8, 9, and 12 on page 187. Let's go ahead and take a look at these. Number 8, when we divide the r's, be careful here, because remember, dividing a fraction is the same as multiplying by the reciprocal. So 6 divided by a half gives 12. Then we subtract the thetas, we get, well, initially, negative 90, which becomes 270, or drop the negative, pull the negative out front. We end up distributing the 12 and end up getting what answer for number 8? Quentin?
Negative 12i.
Negative 12i is correct.
I think
Jamie
I had the negative.
forgot the two. Did you do the 270 thing or did you pull the negative out?
I did the 270 thing.
All right, so you just forgot 270. Remember, is either quadrant 3 or 4,
Yeah.
and sine is negative in 3 or 4.
Okay.
Number 9. This one a little easier. And divide the r's.
3,
Subtract the thetas.
0.
0. So we end up initially with 3 times the cosine of 0 degrees plus I times the sine of 0 degrees. And remember, this doesn't equal 0, does it? What is the cosine of 0?
1,
And the sine of 0,
0,
in other words, just
1, 0.
0, right? So it becomes 3 times 1
3.
and 3 times 0i,
0.
0i, and our answer is just 3. Interesting to note, and we're going to come back to this tomorrow, that is 1. Important thing to memorize. It's a big, fancy, weird way to say 1. Kind of like sine squared plus cosine squared, always is 1. Cosine plus cosine 0 degrees plus I sine of 0 degrees is 1. Now, I didn't for, Andrew's first birthday earlier in the month be like, oh, my little boy's cosine 0 degrees plus I sine 0 degrees today. Oh, this is so exciting. Okay, I'm not that big of a nerd, okay? But it means 1, right? That's just what it is. And that's going to be important tomorrow. Number 12. Divide the r's. What do you get? 7 halves. Subtract the thetas. What do you get? 270.
Yes.
This one's straight up, not a negative 90 or anything that turns into a 270, just a 270. Now remember, sine's negative in quadrant 3 or 4. Well, what do we get?
I got confused. I was thinking that we might need to get a reference angle. So
Well, we do, right? So we end up with the 7 halves times cosine 270 plus I sine 270. It is reference angle.
I was thinking we would need. Oh, wait a minute. I think I see. Would it be 90?
Right, 90. Because either you're measuring from the 180 and saying it's 90 away, or if you think quadrant 4, you're going to say it's 90 away from 360. So 90, quadrant 3 or 4, just like the last 270 we worked with. And the cosine of 90 is
0.
0. The sine of 90 is
1.
1. Don't forget the I, but sine in either of those quadrants.
It's negative.
Negative. So when I multiply the 7 halves by 0 minus 1, I get
We get negative 7 halves I.
negative 7 halves I, or negative 7i over 2. Or if you said negative 3.5i, it's not a decimal that bothers me that bad. Not like weird decimals, but, whatever. Questions on 12? Questions on division? All right. So as we talk about the trig form, again, the initial thought when you first see the trig form is, why? Like, why make up this random form, right? And I show you multiplication. It's like, okay, I can kind of see how that's faster. I show you division, like, okay, yeah, that's definitely faster. Though I still don't know that I would convert a number. For instance, you look at number 10. Am I going to take time to convert that into trig form just so I can divide it? I don't know that that's faster. It probably is still faster just to roll with the conjugate rather than take the time to convert them over first. But consider this. Consider if I wanted to, for instance, take a standard form number and raise it to a power. Let's just say the 4th power. Well, this means negative 2 plus 3i times negative 2 plus 3i times negative 2 plus 3i times negative 2 plus 3i. But in Algebra 2, you're going back a ways here. You're going back to Zoom calls. Okay? In Algebra 2, you learned that we could easily raise any binomial that includes complex numbers in the standard form to a power using Pascal's triangle. You remember this guy? And so on and so forth. And whatever power was present, you take that row, as indicated by the second term of the row, and you start by writing out your coefficients. 1, 4, 6, 4, 1. Then you take the first term and you start it off to the 4th power. So we'd have a negative 2 to the 4th, then a negative 2 cubed, and a negative 2 squared, and a negative 2 to the 1st, and a negative 2 gone. Then we take the 3i, and we'd start the 3i off gone. then it'd be 3i to the first, 3i squared, 3i cubed, 3i to the fourth. And the signs, because of the positive here, would just be positive throughout. Although the -2 might have something to change that, right? And then we had to simplify all of that. And if you did, you could combine like terms together at the end, because of course the I squared is going to give you a -1, and that's going to make this not imaginary anymore. The I cubed is going to end up being a -I, which is going to leave it imaginary. When you get to the I to the fourth, that's going to be a positive one. You combine it all together, and you get a complex number. Or we can do it in the trig form, and we skip all of that. Next section of notes, trig form to a power. Raising to a power in the trig form. No Pascal's triangle needed. Raising to a power in the trig form. And because this was coming, that's why I didn't have you actually do the notes on the other. Consider the trig form for a moment. It's r times the cosine theta plus I times the sine of theta. Suppose we were to raise the entire number to some power. Well, that means that it's this times itself, times itself, times itself, however many times. For instance, let's just say it's 4 times. Well, that means r times r times r times r, which would be r to the fourth. So in other words, step 1 is simply raise the r to the nth power. Number 2, remember what you're going to end up doing with the theta, right? It's going to be the theta plus that theta plus that theta plus that theta. But wouldn't it be faster just to multiply it by 4 or by n? So number 2 is n theta. This is very similar to the way they work with variables. Remember, we said it with a monomial raised to a power. The number, the numerical coefficient, you actually raise to the power. But to raise a power to a power, you multiply the exponents. We've kind of been treating the theta like an exponent this whole time, and we're continuing that. To raise a power to a power, multiply the exponents, multiply n times theta. It's very similar in that regard. Number 3, oh, by the way, you're probably going to need, often will need, to subtract 360 degrees. Often going to need to subtract 360 here. And then finally, convert to the standard form. So for instance, if I had 4 times the cosine of 300 degrees plus I times the sine of 300 degrees, and I wanted to, let's say, cube this expression. Well, we start by raising the r to the nth power. That means we're going to start by doing what?
Raising 4 to, or cubing 4.
Cubing the 4. Raise 4 to the third power. Cube the 4. What is 4 cubed? 64. If you don't remember that, remember the y to the x button on your calculator. We do 4 y to the x 3. Okay? For numbers that maybe we didn't memorize, but that's one we memorized in Algebra 1 and Algebra 2. Then we're going to multiply the theta times the exponent. So we're not cubing the 300, we're saying 300 literally times 3, which is 900. So we get cosine 900 degrees. Well, that's no good, right? What do I need to do with the 900? Minus 360. We're actually going to have to do it twice, right? So minus 360 minus another 360 really gives us 64 times the cosine of 180. Plus I times the sine of 180. Of course, you'll notice that I was far too lazy to write the I sine of 900. And then we do what we always do, convert to standard form. 180 has a reference angle of 0 degrees in either quadrant, 2 or 3, doesn't really matter. What's the cosine of 0? 1/1. But in quadrant 2 or in quadrant 3, doesn't matter, cosine's going to be negative either way. What's the sine of 0? 0. And of course we have the I. We don't really need positive or negative. That's just pretty much nothingness. And we multiply that by 64 and we get questions on that? by the way, cubing this gives negative 64, right? So if I asked you, what's the cube root of negative 64? Well, in algebra 1 and algebra 2, you'd have said, well, the odd root of a negative is negative, and the cube root of 64 is 4. And in algebra 2, I would have told you, there's 2 other cube roots. You just don't know what they are yet. That's one of them. It's a complex number. Anyway, I'm getting ahead of myself. That's tomorrow's lesson. Questions on raising to a power. All right, do you see but are you starting to see where the power, literally, pun somewhat intended, of the trig form comes in? This is where it really becomes next level, if you will. This is where we're finally capping off the algebra training that you had earlier in your year, earlier in your high school years. Let's complete the training. All right, so write this one down now. 2 times the cosine of 15 degrees plus I times the sine of 15 degrees. We're going to raise the whole thing to the 6th power. The 6th power. For starters class, we're going to 2 to the 6th. And that gives us 64. Again. All right, and then we're going to? Good. The theta times the exponent, or 6 times 15 gives?
90.
All right, and then we're going to say, well, 90. What's the cosine of 90?
0.
And what's the sine of 90?
1.
And we distribute, and we get?
64.
64i. And there we go. Questions on that? All right, your seats, I want you to do number 13. All right, so number 13, we're going to start by cubing the 5. That gives us 125. Then we're going to multiply the angle by the 3 to get 90. So, looks very similar. We end up with a 125 times cosine 90 plus I sine 90, which basically gives us 125i. Make sense? I want to go back for just a moment, because we saw what this would look like if I did it the Pascal triangle way, which we did it in algebra 2. It's not the end of the world, but it does definitely take a while, right? What if I converted this into the trig form? What would the r be?
13.
13, square root of 13, correct? And what about the theta? Calculator at the ready.
56.3.
There's your reference angle. So in quadrant 2, I would have to subtract this from 180 to get
123.69.
All right, now keep that number on your calculator for a moment. If I wrote this as the square root of 13 times the cosine of 123.69 blah 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 degrees plus I times the sine of 123.69 blah 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 degrees, all of it raised to the 4th power, you would end up raising the square root of 13 to the 4th power. Well, that ends up giving you the square root of 13 to the 4th. or it gives you 13 squared, doesn't it? Which would be, we know 13 squared off our heads? 169. But on the calculator, multiply 123.69 times 4. And that's too big, isn't it? It's bigger than 360. So subtract 360 from that number on your calculator to get the cosine of
34.76
plus I times the sine of that same 134.76, blah, blah, blah. Put that 134.76 in the memory, and then go ahead and take the cosine. What do you get?
Negative 0.704.
Negative 0.704, blah, blah, blah. Multiply that by 169 to get
Negative 119.
point,
That's it.
That's it. It came out.
comes evenly to negative 119. Now, take the sine of the memory value
0.710.
and multiply that by the 169.
120.
Comes evenly to 120, and don't forget the I. That's what you would have gotten if you'd taken time to do all the Pascal's triangle. Question: was that easier or harder than Pascal's triangle? You think easier? I think so too. I think in this particular process, changing to R and theta, as long as you're careful, the calculator does all the work for you. It's less mental work, it's less writing. And there we go. That's the answer we would have gotten. You can fact check it on YouTube if you want, but that's the answer we would have gotten if we'd taken the time to expand that out. Now your homework this evening is going to be page 187, number 16. Correction, number 14. Page 187, number 14, and a handout. If you're watching on YouTube, the handout is in the description of the video. Okay, so a short handout, just a few problems on the handout, and then also do, and probably on the same handout, go ahead and do page 187, number 14. We'll take a look at all of that in our next lesson tomorrow. Have a wonderful rest of your day, and you are dismissed.